So for today's teardown and analytical detailed look at equipment, we're looking at DLP projectors. Both of these are DLP projectors. One is half dismantled and probably completely dead and has seen many modifications. This will be the one we'll be completely and utterly shredding to bits to see how these things work. And this one is in fully functional condition, and we won't be tearing this one down as much, but we can give a demonstration of some of the principles that we can't on this one. So, no sense wasting time, let's get on with it. So the first part we'll be looking at is the electronics. Now this is the top of the board, and what we have here, interestingly, are these three inductors for noise suppression. Are actually made with a translucent purple epoxy. Here we have two programmable devices. One is a flash. There's actually a number of flash chips on the board. Some good old-fashioned SD RAM. We have a custom DLP ASIC, another Atmel flash. So we've got, essentially this device is going to be running more than one microprocessor and microcontroller, so you're going to need your firmware points. And then we have a nice SD RAM based for, is it SD RAM or is it something? Oh, bloody hell. Don't you just hate it when that happens? I mean, nah. Oh, stupid. Ugh. Now I have to do editing. Grr. Bear with me. Alright, there we go. It's 16 megabit SG RAM, graphics RAM. So this will be obviously for the graphics. We've got BGA footprints, you will soon see why. And if we liberate the board of this metal panel over here, we have the very bottom of the DLP chip and more components. We have another custom DLP ASIC, as well as a number of small more jelly bean logic devices. No I2C devices, surprisingly, and some 7.4 jelly bean logic. Here we have the button interface, which is nothing particularly amazing. It looks entirely passive, and if we're lucky might contain a multiplexer. But it doesn't, it's an entirely passive system. It has some status LEDs though. The switches are labelled to various points. Another point of note is some unpopulated connectors. So we have this one, which is unmarked, so we're not exactly sure what went to this. And we've got one for a fan and speakers. Of course, a fan has been soldered directly to it. On the other side is where it starts to get interesting, but there's also a fair bit of custom stuff. This little chip here is an Atmel AT89C52. Be a random Atmel microcontroller, which is also right near the actual light sensor that the unit uses to keep track of whether the actual light's working, as these things will generally automatically shut down if they don't detect the light. Here we have a 3-phase DC brushless motor driver. Well, it might not be DC. Here we have the actual DLP chip itself, probably going to be a Texas Instruments unit, as Texas Instruments have quite a monopoly hold on DLP technology, but then they did invent it in the late 80s as well, 1987. It came into commercial use, I think, in about 1997. Here we have the main DLP custom ASIC. We can find nothing on these custom ASICs. Some more RAM that goes with it. Another DLP ASIC. What I believe to be the main brains of the business, the actual main microprocessor, although once again, no data, only part references online. Here we have another unknown custom ASIC. We have no clue what that does. I don't even have a vague idea. And this is also another unknown custom ASIC. Here we have an analog flat panel display adapter. Now interestingly, this thing has a DVI port, but there doesn't seem to be a DVI chip, so this is actually quite strange. And also, the latest date code is of that of 2002. Yeah, it makes sense, because we've got made in the United States of America, which means it's obviously early projector technology, well, early 2000s, when this stuff was still very much new to the commercial market, and it was very much being built in-house by the manufacturers before it got outsourced. But interestingly, that seems to be a purely analog chip, which I was not expecting. This one is your main video driver IC. This takes all your composites, RGB and all that. And it is also compatible with CCAM, NTSC and PAL. Now, one thing I really love about the design of this is the standard chip crystal it uses to comply with the standards. It's removable. It's just plug into a socket, which actually makes which is actually really good for manufacturing. And even if you take this abroad, because you can just swap out the crystal to whatever your standard in your part of the world uses. It's a bit of a shame we have to have our multi-video standards, but that's the way it is. Here we have a nice IR sensor, which also links to this little 4-pin device here. I can't quite see what it is. It's an LM317, so an op-amp basically. We have this unused unknown connector here. However, we do have 4 test points, potentially a serial interface. You do get these sorts of serial interfaces, although whether this is worth plugging into the power and debugging, who knows. But the real point of the business is the DLP chip, which is in this lovely plastic bezel, and if we just gently pop it out like so, we can see the back, and it uses zebra strips. Now, for those of you who don't know what zebra strips are, they're basically a silicone rubbery substance which contains small conductive bits of metal internally. You might be able to see it if the camera focuses. Come on, focus. Okay, the camera's not going to focus even with pressing the focus button. So that goes in there, and it provides a nice conduction. That's pretty much the motherboard. Aside from a rather nice DLP chip, complete with a heatsink which is bonded on right here. But obviously these things take quite a proportion of the heat, and despite the fact the sensor's actually shiny and will reflect a lot of light, they will be susceptible to getting hot. That's why I'm quite surprised there wasn't a larger heatsink on the back, but we get into more details of that when we get into dismantling the other one. As a note, this is your main power connector into the motherboard, which will contain the 5V, 12V, but it shouldn't, I don't know this for certain, send in the 300 volts. To be honest, I see no point to this board which is designed to take that kind of voltage. Not unless you want to turn it into fireworks. The alloy case, internal chassis that holds it together, looks like it's made out of cast magnesium alloy, because if we got the classic MG, which is the atomic symbol for magnesium. Correct me if I'm wrong, but I don't believe I am in this case. Hehe, I do remember some periodic table elements. But yeah, sadly we don't have a blowtorch, so we can't do anything fun with this. The next part of note is the power supply, which is your standard switch mode affair, but it's made out of a lovely fiberglass PCB. We don't have any slot isolation, so we're reliant on pretty much PCB clearance details, but we do have an isolation slot which goes all the way to here, and then there's this random ground plane which goes whee down to the live side. So this is not necessarily a fully isolated design. And then on the power outputs we have 300 volts, 12 volts, and of course your mandatory 5 volts, 3.3 volts, and there's even an oddball 8.5 volts. And we're about to run out of memory. Grr. Back to where we were. Hopefully I don't repeat too much. But my mind does tend to wander when the card's doing download. We've got a lovely bank of smoothing capacitors which are made by Nippon Chemicon, and they are all 16 volts, 680 UF, so a bit of an odd value in the microfarads. Here we have an opto isolator. I believe either this section or this section is the 300 volt output, but I haven't actually applied power to this to test it. Now we've got our usual sort of input MOVs and mains filter capacitors and inductors, and a nice anti-rupturing fusing, which looks like it should be a 5 amp fuse. Our two main input power transistors, which are on the live side, and our two main filter capacitors, which are 200 volt, 470 UF. Of course they're in series for us Brits and Australians and everyone who uses nice 240 volt power rather than a wimpy little 115 or 120 that will power diddly squit. Here we have our main isolation transformer, so on and so forth. One thing you might be noticing, Rubicon, is this whole unit has a very nice high quality construction to it, which is something you don't always come across in even stuff like this, but this is actually really quite nice. They've got some nice little transistors. In fact, actually these are labelled D, so these could be diodes or diode networks rather than transistors. Here's the main bridge rectifier, the sort you'd find in your PC power supply, so it's a fairly high power one. There's no wattage markings on this, but one thing is where is it? Country of origin, Philippines. So this was made, country of origin, Philippines. So this was probably made by Filipino boys. And good job to you, because you've done an excellent job building and designing this power supply. You know, the earth goes off straight to chassis ground, which is the magnesium chassis, internal chassis, because these things are mostly made out of plastic externally. Nice standard IEC kettle lead, we like these, and so on and so forth. And there's decent isolation. Okay, maybe a few isolation slots and that would be nice, and that particular ground plane maybe not the best, but we do have a 4-layer board marking, meaning that salvaging components off this board will be an absolute pain and agony. Right, onto the optics. Now the optics is where this thing really starts to get interesting, because the DLP chip, if we can find, will mount in here something like that. So that's where it comes in. But if we get our torch and shine it in from where the light from the xenon arc lamp comes in, you may notice it comes up at an exact angle, and the point at which the chip's facing, so it comes and then comes out at a slight angle, and the point at which the chip's facing directly up, and to repeat myself without knocking over that, and the point at which the chip's facing is the output. So once again we've got some funky prism optics in there, which is something we always like to see. The only thing I'm not 100% sure of where it is the beam dump. Because as with these, there has to be an area where the unwanted light energy is dumped, where it doesn't output to the screen or back to the xenon arc lamp. You know, they already run hot enough. But this point here is where the colour wheel would go. Colour wheels are used on single chip designs. And that's a consistence of the standard sort of French colour scheme. So you get your sort of reddy, orangey colour, you get yellow, and you get this blue that they call crayon or something. Now here, this little point, which looks like it has an IR filter or something on it, we have is the point that the boards, remember that sensor on the board? That goes through there, so the board knows when it's switched on. And then here we have our actual focusing optics. So let's actually start pulling this down and actually seeing what's inside this prism. Everything's a bit dark in here for me. You see I've got eye protection on. These lamps output a heck of a lot of UV, so you don't really want to be viewing them directly, at least not for long periods of time. Here we have the working one projecting onto the wall here. It's out of focus at the moment and is too close to be in focus, even when we adjust the size of the thing. So if we look in here, where I'm zooming up on, you can see the colour wheel. This little unit is what essentially does the colour for a very clever concoction of multiplexing. The DLP in this unit is right at the back there, and we also don't seem to have so much Texas Instruments branded stuff, but then this is made by Sharp. But you may also notice this is very much a newer unit because the optics are also a lot simpler. And then that big unit there is your xenon arc lamp. And then of course you got your front HV boards. That board there I'd imagine would be the HV board for it, and then there's more power supply underneath the motherboard. One thing you might be able to notice is there's a fly's eye effect when you shine through there. I don't know how well the camera picks it up. But going back to the sensor as part of the optic, this little glass prism here, which is sometimes just a point of mirrors, it actually helps create, it does a similar sort of thing to the things you used to hold to your eye as a kid, and then you twist them and you'd see all the beads go around, they'd make pretty patterns. Well, it works on a similar principle to this. Then it goes through essentially a convex lens system, which is actually two lenses in one particular module here. So once again we've got some nice optics. Then that feeds into there, which creates a fly's eye lens effect, essentially without having to use the space of using an actual fly's eye, which would extend the size of the mechanism. But fly's eye lenses can be found in 3-element systems where size isn't such an issue. I'll put a link to Mike's Electric Stuff teardown of a 3-element unit if you're interested. This little light pipe essentially will use a principle known as total internal reflection, which is the exact same principle used in fibre optical systems for optical communication. It consists of that there's a certain angle that when you shine the light into a tube, 100% of the light will bounce off and reflect internally without escaping outside. Hence the effect, hence the name of total internal reflection. There is some relatively complicated maths behind it, but it's nothing like RF where it goes completely into unintuitive territory. The section that does the major screening has a total of 2 separate prisms, as can be seen here. We have this prism which reflects the light upwards in a sort of diagonal direction to the sensor, and then this prism which then reflects the light out through to the main lens optics for projecting it onto the nearest wall. Now interestingly, I still have not found an area for a beam dump, so I can only assume the beam dump is essentially the sides of the housing, as there is no specific heat sink. Now, sometimes you can come off and things like the actual deposity paintwork of it, original factory paintwork, is actually bleached off because of the severe amount of UV light. Now these are fairly well glued in, so extracting them will be a fun challenge. So if anyone's got any good suggestions for what to do with funky optics like this, please put a note. I'd quite like some good scientific experiments with some optics like this. I managed to extract the prism optics mostly intact. There's a few dings here and there, but under the circumstances I reckon I did well. And of course we've got another nice magnifying lens. Maybe we can make some sort of super macro mode. And one really fun thing to do with prisms, shine lasers through them, of course. And you can get some really funky effects. You can make some sort of neat laser light show of just a motor and just a little motor. And then the last lens module, which isn't really worth tearing apart, consists of at least 5 lenses, but you've got 1, 2, 3, 4, 5, technically 6. And you know it's good optics when it says it's made in Japan. Thumbs up. So you've got a bit of a conclusion for all sorts of areas around the world. I don't know if there's any parts manufactured in Europe, but then you'd have all the main continents. Let's take a look inside the more complete unit, which is all fully functional. We can once again see the path of the optics, and it is a lot smaller because the path of the optics of this one is pretty much fits in the same sort of area as the whole lens assembly of the one we just tore down. Look at that. Oh, we could make a nice macro lens here. But the path comes straight from the xenon arc lamp down here through the colour wheel, which is visible here, and you can see this sort of reddy colour. If we take off this rubber spacer, you can see the colour wheel a lot better. You can also see where the UV light has bleached the metal, removing the colouring. And then it goes through here. There'll be some nice prisms here to bounce into the DLP chip, or DMD chip as they're also known. DLP stands for digital light processing. And then it will bounce back out through the lens optics to be focused on a nearby wall. This unit here looks like essentially the flyback board for the arc lamp, and you've got some big thick wires disappearing under this main motherboard here. We've got another little board here, and we have a load of diodes lined up on that board, so we might potentially have a voltage multiplier. Now this has pixel work, so this one's got a different company behind it, so this might not be all a TI DLP chip like this one. We also seem to have 3 fans in the units. One here to blow the excess heat out from the light housing, another one here for the electronics and power supply, and then a blower fan here, which will be more cooling for the light essentially. And that's really all we can see when we look in the top here. We'd have to pull it down further, and looking at how compactly put together this thing is, I'm not really willing to at the moment. Under here, we'll just shine a light in, we have the main power supply, which I'd imagine will go to a certain degree of the high voltage stuff to power this up. Now this has to use a very clever version of multiplexing. Essentially this has to display 3 images for 1 frame for each of the 3 main colours, sometimes more because sometimes they put a yellow point in, but these are always glass, these colour wheels. And so what these do is they actually like little mirrors, so take this, they point one way and point the other way to make a picture, obviously focusing it out towards the lens, point the other way to reflect it off to the dump. They also have the little speaker there. Yay, I know what a speaker is. Don't think it's stereo. And so these billions of little mirrors, or millions of them, will flip in either on or off position. There is a bit of tarnishing to this mirror, unfortunately. The principal operation of how they work is actually quite simple, however, as all in practice, implementation is a lot more complicated. Good luck building one of these at home. If you manage it, thumbs up to you. Sadly, you can't really see any of the actual driving electronics that will be housed within the die, but this is one very beautiful chip. We have a new contender for the EEPROMs and CCDs in my books. But as for a look at the secret life of DLP projectors, we are done here. And if anyone has any really good, interesting and scientific ideas on what to do with the optics, because optics are always fun, please do throw some suggestions across, because I would quite like to play with these optics. I'm just not sure exactly what to do with optics and what experiments to perform. Maybe there could be some good videos there. Thanks for watching. Hope you enjoyed. Hope you also learned something. But there's always something to learn.